The Great Digitization moved millions of textual records from physical archives onto digital servers. Researchers now access massive temporal spans of human writing. To process this volume, the field of cultural analytics relies on distant reading, using algorithms to scan the data and identify broad statistical patterns and frequency spikes over time. But algorithms that only count words hit a strict limit. They strip away context. A frequency graph shows that a word became popular, but it cannot explain the nuance, intent, or the specific human argument behind its usage. Traditional hermeneutics, the practice of close, deeply contextual reading, captures that human intent perfectly. Yet a single researcher cannot physically close read 10 million documents. This leaves a chasm in modern research. On one side, massive but shallow data processing. On the other, deep but entirely isolated human analysis. Unless we build a method to connect massive data trends to genuine human meaning, our historical archives will remain analytically inert. This graphic details computational hermeneutics, a 5-stage pipeline designed to cross that chasm. It organizes raw discourse into a structured, multi-step interpretive process. The ultimate objective is to map abstract textual shifts onto physical reality, tracking exactly how linguistic changes fund new universities or draft policy frameworks. It gives analysts a measurable mechanism to monitor how language and ideas ultimately shape organizations and societal structures. By structuring this progression, computational hermeneutics turns language analysis from a retrospective academic exercise into a predictive tool for institutional foresight. The first stage of this framework begins by ingesting deep temporal archives to isolate initial cultural and linguistic signals. This diagram illustrates Stage 2's continuous, cyclical workflow. Automated models detect structural anomalies, routing them to human researchers for contextual synthesis. That analysis then feeds a data refresh phase, actively updating the digital corpus parameters with new findings. Static algorithms fail because language constantly drifts. The exact meaning of a single term in 1950 rarely matches its meaning in 1990. The cyclical architecture forces computational models to constantly recalibrate against historical context, anchoring the statistical findings in specific human meaning. Stage 3 addresses a distinct mechanical problem, filtering massive macroscopic word counts into microscopic targeted analysis. Looking at the top band of this schematic, the initial input consists of macroscopic scale, raw corpora, and topic modeling. It must pass through the analytical mediation layer, where geometric filters sort the raw frequencies. Algorithms execute keyword and context analysis, locking isolated terms into their original sentences. This precise sorting extracts semantic prosody, calculating the specific network of meaning, emotion, and valence a word accumulates. Only after this filtration is the data passed to the analyst, arriving as relational structures and network maps. By filtering massive volume into relational nuance, this translation interface proves that algorithmic pattern detection can directly support nuanced historical explanation. Stage 4 isolates what happens when semantic prosody permanently alters the accepted meaning of a concept. The central node of this topological map represents the epistemic shift, the exact threshold where an idea graduates from mere discourse into stabilized reality. These shifts originate from noisy, overlapping wave fields of localized cultural data. As time compresses, changing valences push semantic vectors into established trajectories. Eventually, the discourse materializes. Institutional crystallization occurs when a new way of speaking directly yields a physical laboratory, a new academic department, or a funding change. Crucially, the retrieval layer at the bottom left proves the connection. It maps every real-world institutional change back to the exact historical texts that sparked the semantic drift. Societal change is not spontaneous. Through this topology map, structural shifts become traceable consequences of prolonged semantic evolution. The fifth and final stage operationalizes these models, shifting from analyzing history to forecasting organizational change. On the left side of this dashboard, the discursive signal layer provides a baseline, tracking the emergence, stabilization, and fading of specific topics in publications. Because the framework mathematically correlates these publication dynamics with real-world technological materialization, arrows map textual momentum directly into physical reality. Organizations can utilize these specific correlations as early warning indicators for impending industry shifts. The direct output is an evaluative detection dashboard capable of generating actionable, predictive intelligence on future organizational adoption rates. By tracking how semantics institutionalize, organizations can proactively adapt their resource allocation long before market disruption takes hold. This complete pipeline processes thousands of historical texts, structures the data, and refines it into a predictive strategic dashboard. It successfully marries the massive quantitative scale of machine computation with the deep contextual validity required by humanistic interpretation. Unlike black box predictive models that obscure their reasoning, every single insight generated here possesses absolute corpus-level traceability back to the original source. Ultimately, this framework establishes a strict operational fusion between massive quantitative volume and profound qualitative depth. This framework provides a method for tracing current semantic drifts to identify where and how future institutional shifts will occur.